This is a tutorial on a mode of ventilation that was developed to help the patient breathe spontaneously through an endotracheal tube or tracheostomy by reducing the work of breathing. It can either be used as a standalone alternative to pressure support or be used as part of a pressure-limited strategy of mechanical ventilation. The tutorial is about automatic tube compensation. Automatic tube compensation. In this tutorial, I'm going to discuss the problems of pressure dropping across the length of an endotracheal tube and what it means for the patient. And then I'm going to explain the concept behind automatic tube compensation and how it works in different ventilators. Let's start with a clinical scenario. You're in the ICU and you come to see Philip. Philip was in the operating room this morning. He had a difficult intubation and he had significant airway trauma and eventually was intubated with a size 6.5 endotracheal tube. This is a very small tube for a male. It should really be an 8 or an 8.5, very, very small internal diameter. Now, Philip has normal lungs, but there is no cuff leak that's indicative that he has quite significant airway edema, so he's going to be stuck with this tube in his throat for the foreseeable future. Now, Philip is beginning to wake up and breathe spontaneously, and the question that arises is, with such a small endotracheal tube, what ventilator strategy should we use? Just a quick bit of revision. Inspiration happens when the diaphragm descends and negative pressure is generated inside the thorax. That causes negative pressure to be generated in the alveoli and gas flows from the mouth into the alveoli along the pressure gradient. Expiration happens when the chest wall and diaphragm relaxes and there is elastic recoil and gas is expelled from the alveoli through the mouth because the pressure in the thorax is higher than the pressure in the alveoli, and the pressure in the alveoli is higher than the pressure in the airway, and the pressure in the airway is higher than atmospheric. When we look at work of breathing, there are two components that you need to understand. The first is the concept of resistance work, and that is the work that's done to move gas through ever narrowing airways all the way down to the alveoli, starting at the pharynx through the larynx and then all along the tracheobronchial tree. And then secondly, there is elastic work that is required to move the diaphragm and to lift the lungs and the chest wall and the pleura upwards and outwards. In this scenario, we have a patient who is intubated and there's an endotracheal tube in the trachea, and I've drawn a small number of alveoli, and you can see that there is slimy material in the airways. Some of the airways are inflamed and there's some hydrothorax, that's a pleural effusion, some pulmonary edema. When the patient tries to breathe here, they take a breath, their diaphragm descends, and they have to drag gas through the endotracheal tube and then open up their lungs. So in this case, the elastic work is the same work, except it's higher because the lungs are diseased and there is edema and inflammatory material in the lungs, so they are heavier than they would normally be. But the resistive work is also increased because the patient now has to breathe through an endotracheal tube all the way into the airway and then breathe along the airway. So there's a significant increase in the amount of airway resistance. When the patient exhales, then gas is pushed out of the lungs, but also that gas has to move through the same endotracheal tube, so there is resistance work on the other side of the breath in exhalation. Now we know that when we put a patient on positive pressure ventilation, there is a high pressure at the connection, but that pressure dissipates as it goes along the endotracheal tube. So there's a significant loss of pressure from the beginning until the end of the endotracheal tube. And that is what this tutorial is about, how we can figure out what that loss of pressure is and how we can compensate it to make the patient feel comfortable when they're breathing spontaneously. The first point I want to make, though, is that increasing gas flow rates increases resistance through the tube. So if you look at a person who is breathing normally, if you breathe through your normal airways and you breathe small breaths that are small tidal volumes, it's very easy to breathe. The harder you breathe in, the bigger the breath you take, the higher the flow, the greater the pressure drop along the airway, and the more harder it is to get gas in because of increase in turbulence of that flow and increase in airway resistance. This obviously gets worse when you place an endotracheal tube. But if you put a large endotracheal tube like a size 9, it's not that much worse than breathing through normal airways. But look at the shape of the curve. The curve is non-linear. The airway curve is pretty linear looking, but the tube curve goes up, 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 and then basically goes straight up. And that's because the tube has quite a small internal diameter, even if it's a big one. And the higher the flow rate, the higher the resistance, and the greater the amount of pressure that is required to maintain flow through that endotracheal tube. Obviously, the smaller the internal diameter, the greater the pressure drop per unit flow. And so an 8mm tube has a bigger pressure drop, 7 is greater again, 6.5, 6, 5. And what I'm trying to show here is, and you know this if you've ever tried to breathe through a straw that you get with a drink, the fatter the straw is, the easier it is to breathe through. The thinner the straw, the harder it is to breathe through. And so the narrower the gauge of the endotracheal tube, the harder it is to breathe through, and the greater the pressure drop per unit flow for the patient. I don't want to torture you with all kinds of material on maths and physics, but you do need to know the equation of motion. And that is the driving pressure equals the flow times the resistance. Remember, higher the flow, higher the resistance, plus the elastance times the volume. The driving pressure, of course, is the pressure that's generated by the ventilator. That's positive pressure, plus the pressure that's generated by the patient or the patient's muscles. That's a negative pressure. You put the two of them together. So 10 centimeters of water by the ventilator and minus 5 centimeters of water from the patient equals 15. The flow times the resistance are the resistance forces, and the elastance times the volume is the elastic forces. To clean this up into nomenclature that we've used before, we talk about the driving pressure equals the flow times the resistance plus the tidal volume divided by the compliance. The compliance goes from 0 to about 100, so the greater the compliance, the greater the tidal volume. Let's return to this model. In this situation, we have a spontaneous breathing patient. Now, without any additional support, the pressure that generates flow into the airway is derived entirely by muscles. The patient generates negative pressure within the thorax and gas flows along the pressure gradient. In the process, it must overcome both resistance forces, that's particularly a problem with the endotracheal tube, and elastic forces that are determined by the total respiratory system compliance. Now we decide that this patient needs pressure support. The lungs in Philip's case are normal, but the endotracheal tube is narrow. So the pressure support is targeted at overcoming tube resistance. And the plan here is that the pressure at the end of the tube is the same as the airway pressure, so that the patient feels that they are breathing normally through their mouth. There is no additional work to breathing from the endotracheal tube. In this scenario, the patient is on a pressure support of 7 and a PEEP of 5, and the tube is a size 7.5, and that is believed to be about the right combination. So the pressure support of 7 should be enough to overcome resistance through the tube, such that at the end of the tube the patient is receiving CPAP without any additional support. In other words, the patient feels that they're breathing normally through their mouth. But how can you be sure that the patient is receiving sufficient pressure support, which is the most important component, or whether or not they're getting too much? In this diagram, we're going to plot pressure versus flow, and you can see that the relationship is non-linear. As we increase flow rates, we increase resistance. So let's draw a line for PEEP. Now, it would appear to me that the ideal flow rate here is about 45 liters. Beyond that point, pressure support may be inadequate to compensate for flow resistance combination. Below that point, pressure support may be a little bit excessive, but that's not really a problem. You may recall this picture that mapped out the airway pressure as it is measured by the ventilator versus the alveolar pressure that is delivered to the airways. I am now going to show you another pressure, the tracheal pressure. This patient is on pressure support ventilation with the pressure support inspiratory pressure of 10 and a PEEP of 5. The airway pressure curve that I've drawn for you here is the same flat top picture that we have visited many times before, but now we're going to look at the tracheal pressure. And you can see that when the patient takes a spontaneous breath, the tracheal pressure drops slightly below PEEP, the ventilator generates a flow of gas, and the pressure rises up to the pressure limit before drifting back down again. Now in this situation, the patient is on the same settings, inspiratory pressure of 10, PEEP of 5, but they take a larger inspiratory effort. This results in a significantly greater drop in the tracheal pressure during inspiration, evidence of increased work of breathing. The fixed pressure support level is inadequate to match the continuous changing patient demands. And this is the major flaw of pressure support. Although flow is technically unlimited, the pressure level is fixed, and that means that every breath receives the same amount of support whether or not it's really being demanded. Big breaths, small breaths, same support. Can anything be done about this? Well, yes, there is an adjustment to pressure support that began appearing in ventilators in the early part of the 21st century, and that is known as automatic tube compensation. This is a setting, it's on several ventilators, and the idea is that it repurposes pressure support style breaths to be more adaptive to patients' needs, and the major goal is to eliminate resistance work through the endotracheal tube. Now it is used in some ventilators in more advanced strategies to boost the pressure support and inspiration and actively assist expiration in order to reduce the overall work of breathing. And what it does is it adjusts flow and pressure to either avoid undercompensation or overcompensation due to the tube resistance and the pressure drop across the tube. And consequently, the tracheal pressure is kept constant. And it does this by rapidly sampling the flow and pressure waveforms at 500 Hz and dynamically adjusting the flow and the pressure to match patient demands and to adjust to the calculated tracheal pressure. Implementation of the concept of automatic tube compensation is different from brand to brand. And on Puritan and Bennett ventilators, ATC or automatic tube compensation is an alternative to pressure support, usually for patients requiring minimum support, for essentially patients who are more or less weaned, but they still need to be on the ventilator. And this is what automatic tube compensation does in this setting. Essentially, the flow through the endotracheal tube is determined by forward pressure generated by the ventilator and the inspiratory effort, and back pressure consequent of airway resistance and PEEP. The purpose of automatic tube compensation or inspiration is to instruct the ventilator to generate sufficient forward pressure to offset that back pressure during inspiration, to ensure that the patient does not sense that they're having to work hard to inhale. Let's return to this scenario again. This is the picture I showed you a few minutes ago with pressure support, and now we're going to change the patient from pressure support, where they're struggling, to automatic tube compensation. Now, this looks very different. The airway pressure waveform looks sinusoidal, which, as you will recall, is what you see with spontaneous ventilation. The patient inspires and the tracheal pressure remains relatively constant. And although the airway pressure looks reasonably high, this reflects the early initial high flow that decelerates along the sine wave. The key issue here is that the work of breathing subsides. How does the Puritan Bennett ventilator know what adjustments to make? Well, built into the software is this chart and it uses the chart to dynamically change pressure depending on inspiratory flow. If the flow increases, pressure increases. And it measures the flow rate every 5 milliseconds to adjust the flow to pressure relationship for the specific airway based on the chart. So you've told the ventilator what airway the patient has, and then it figures out using the chart what it should be doing. And you can see here that the patient like Philip, who has a 6.5 endotracheal tube, this is the chart that it uses. There is a second chart, of course, for tracheostomies. Now let's look at how to set up automatic tube compensation, ATC, on a Puritan Bennett ventilator. The first thing to state is that ATC can be used on this ventilator as an alternative to pressure support anytime that you might use pressure support. In this situation, this patient is on one of the SIMV modes, and normally when you put someone on SIMV, you specify pressure support. But in this patient, we're going to put the patient on tube compensation. The next thing that you absolutely must do is tell the ventilator what type of tube the patient has. And in this situation, we're telling the patient that the tube is an 8.5 millimeter internal diameter endotracheal tube. That's the bit on the bottom. Imperative to make sure that this is the correct tube, ET tube, not tracheostomy, and vice versa. Then you need to set the amount of support that you're going to give the patient. I always start with 100%. Why wouldn't you? And then if the tidal volumes are excessive, then you can dial it down. What you don't want the patient is struggling to get a sufficient flow from the ventilator. And finally, because it's a pressure support style mode, you set an expiratory sensitivity. Now let's move on and see what this looks like on the vent screen. This is a patient on pressure support ventilation. You can see here that the patient is on fairly low settings. Curiously, even though you've probably seen screens like this a million times and think they look okay, there's a few things going on here. First of all, this patient is dragging nearly 60 liters of flow from the ventilator, and the pressure waveform itself is a little bit suboptimal. You can see there is a terminal spike on it. That means that the E-sense is probably a bit too long for this particular patient. But let's flip this patient over onto tube compensation, and all you got to do is on the settings screen is instead of pressure support, push TC and 100%, and you end up in this situation. So you can see here we're on tube compensation. These are the settings, very much the same as we're on pressure support, but instead of specifying a particular pressure support level, we've dialed up a support level of 100% on tube compensation. And you can see here it all looks a little bit different. The waveform is very roundy looking, right? So this pressure waveform is much more like what you see in CPAP versus what you see on pressure support. It kind of gently guides upwards and then falls away again. And the flow waveform itself, even though it is a decelerating flow waveform that shaves off at 25% of peak flow, it's ever so slightly different. So as an alternative to pressure support, it would seem to me for a patient who is weaning from the ventilator that it's a pretty elegant alternative to T-piece for a spontaneous breathing trial. There's a dramatic loss of control for the operator, and there's always a bit of a question about what you do if the tidal volume is inadequate, because you cannot increase the automatic tube compensation over 100%, so you need to go back on to pressure support. And what do you do if the rapid shallow breathing index is more than 110? Now, I haven't discussed this in detail in the course yet, but this is an index of how distressed a patient is. And if a patient is 40 breaths per minute and they're struggling, well, it clearly isn't doing what it's supposed to do. But it is available on a lot of the ventilators, and patients seem to be very, very comfortable on it. And even on the more complex ventilators, such as the Draeger ventilators, you can give them this mode as an alternative to pressure support by just setting the pressure support at 0 and let the machine do its magic. On Draeger and Hamilton ventilators, ATC is a little bit more complicated because it sculpts the pressure waveform to ensure that the tracheal pressure is maintained in inspiration and expiration. And in both situations, the work of breathing is reduced. On inspiration by overcoming the pressure drop along the tube, and in expiration by increasing the pressure drop along the tube. And it is used alongside all of the different modes of pressure limited ventilation that are on these two ventilators. Now I want to explain what I mean by expiratory support. In this cartoon, the patient is getting ready to exhale. The PEEP is 5 throughout the breathing system, from the ventilator on the right hand side to the alveoli on the left. Remember that exhalation is by elastic recoil. Relaxation of the diaphragm increases the pleural pressure, that increases alveolar pressure, and that propels gas out of the lungs. The greater the pressure drop from the alveoli, the more efficient ventilation is. The problem here is that one is exhaling against an obstruction, in this case an endotracheal tube. Automatic tube compensation dynamically reduces PEEP on the expiratory ventilator limb to make it easier for the patient to exhale, but crucially, the tracheal pressure does not drop, so PEEP is maintained inside the lungs. It is worth noting that a similar technology is used on some non-invasive ventilators. In this case, this is a clipping from the user manual for the Philips Trilogy, and that allows a pressure drop in exhalation to make it easier for the patient to exhale, and they call that C-flex. And the idea of this is that the patient can exhale downhill, particularly those with obstructive sleep apnea. It's adjustable, there are different levels of it, but crucially, the pressure rises back to CPAP level at end exhalation. In this situation, we have a patient on pressure support ventilation where automatic tube compensation has been added on inspiration and expiration. First, we can see the view of the airway pressure as it is seen at the Y. Note that on expiration, the pressure is dropped below the PEEP level in order to facilitate exhalation. On inspiration, there's a little hump, and then it flattens down to that flat top picture that we're used to seeing. But if you look at the tracheal pressure, it's completely different. It's more like what we expect to see on a pressure waveform. The tracheal pressure does not drop below the PEEP, and that little hump is much smaller than you would expect. Here we have our inspiratory support, and here we have our expiratory support. And what they've both done is improve the dynamics of breathing during inspiration and expiration. Importantly, the alveolar pressure is kept constant, and it does not mirror the upward and downward humps on the pressure waveform that are associated with automatic tube compensation. So even though the waveform looks a little bit ugly, what's happening inside the lungs is very reassuring. This is a Draeger screen, and the patient is on pressure controlled SIMV. You can see that automatic tube compensation has been activated, as has pressure support, and you can see here that the endotracheal tube size has been specified. What is noticeable here is that the ATC sculpts the pressure support breath. There is a green line indicating the airway pressure as it would be without ATC. Importantly, when we're using ATC in pressure limited modes, there are very few published papers that show that ATC improves outcomes. But you know what? This stuff is really hard to prove because everybody has different ways of managing their patient. Every patient is different. And so saying that there's no evidence to support it really kind of misses the point. It is a tool in your armory that you can choose to use, and it may make your patient more comfortable, particularly when they're struggling at low levels of vent support. So there's very little to be lost in my view by activating ATC, particularly if you're using a Draeger or Hamilton ventilator. The potential gain is significant, and biphasic ATC is applicable in most spontaneous situations, and it may benefit slow weaning patients as an alternative to pressure support if it's only being used with zero pressure support or minimal pressure support. So what about Philip? Philip was in the operating room, difficult intubation, big airway trauma, intubated with a size 6.5 endotracheal tube. He's normal lungs but no cuff leak, and he's waking up now and breathing spontaneously. The alternatives here are automatic tube compensation or pressure support, or both. At least theoretically, ATC should be more comfortable for the patient. So let's review this tutorial. In this tutorial, I discussed automatic tube compensation. We looked at the pressure-flow resistance relationship. We discussed loss of pressure along the endotracheal tube. I discussed ATC as an alternative to pressure support, and biphasic ATC as a complement to pressure-limited modes of ventilation. So that was automatic tube compensation. I hope you found that useful. If you're enjoying these tutorials, don't forget to follow me on YouTube and subscribe to my channel, or follow ccmtutorials.org.